about random number generator. So we will have 3 talks, 5 minutes each, and then we have 15 minutes time for discussion. So we start with a presentation by Thibaut Michel, and he's presenting a work which was made by an international consortium from Australia, Italy, and France. And it's about real-time self-testing quantum random number generator with non-classical states. Please, Thibaut.
Thank you. Before I start, let me just thank Christian, Serge, and all the other organizers for this conference and for giving me the opportunity to give this talk. Also, it's my first online conference, so I think the organization was really well done. All right, so I'll present this experimental work that's been done at the Australian National University. And it's on a real-time self-testing quantum random number generator with non-classical states. So let me start by explaining the protocol. So this falls into the category of semi-device independent QRNGs, and semi-device in that we don't trust the source of entropy of the QRNG, but we trust the measurement device. And so the protocol is as follows. We'll randomly measure either X or P, these 2 POVM, that corresponds to 2 conjugate quadratures of the state. And delta X, delta P refers to the precision of the POVM measurement, and K is just for labeling the bins. And the idea is that by measuring the P quadrature, we'll be able to estimate a bound on the mean entropy of the conditional mean entropy of the X quadrature, which quantifies how much true random numbers you can extract from this X measurement. And this is done with the entropic uncertainty relation that relates the mean entropy of X and the max entropy of P. And this C here is just a constant that depends on the maximum overlap between the 2 POVMs. So with this, you can form this lower bound that just depends on measurement of the P quadrature. So then when you measure P, you get this estimate. And then when you measure X, you can extract a secure random number from that. So the assumptions of these protocols are that we trust the measurement device, as I said, although you can afford to not trust the classical noise, because you can take it into account as mixedness of the input state that you measure. And then the assumption on the source, they still remain an IID assumption for estimating this max entropy. And also you have to assume that it's bounded, this source, because the entropic uncertainty relation only works for POVM that spans the entire phase space. All right, so here's another scheme of the protocol. And the main feature is that everything was done in real time. So the data acquisition, the entropy estimation, the hashing. Also, we had this active quadrature switching. So the local oscillator was alternatively locked to X or P and randomly. And we also had some mechanical beam blocks to measure shot noise and dark noise. So this whole QRNG was self-testing and self-calibrating in that sense. And we ran it with a non-classical source, so squeeze state of light, and show that it improved the amount of randomness that you can extract. So to start off with, we tried some thermal state source that we generated with phase and amplitude modulators. And here are the results. So we run the protocol, and I'll show on this graph. So the blue line here is the theoretical estimate of what the bound should be for a thermal state with a given variance. The red line is the unconditional mean entropy. So that's the amount of randomness you would extract if you trust the source state. So if you assume there's no correlation to malicious third party. And then the dashed line is just a simulation of the theoretical low bound for if you take into account the finite sample size. So in other words, the bottom line is trusted randomness and the top line is the untrusted randomness. So we run the protocol, and at some point we estimate this lower bound and find this value here for a given thermal state. Then it will go to the other quadrature, extract random numbers, and then estimate again. And so we have this cluster of points, and then we run it for several different types of thermal state with different variants, and this is what we get. So this sort of validates the idea behind the protocol, is that when the variance of this thermal state increases, the apparent randomness in the signal increases, as you can see with the red line here, but the amount of trusted randomness should decrease, because the amount of noise you see could be just correlated to a third party. And then we ran it with the interesting state, which is the squeeze state source, which was generated with OPA cavity. And the idea here, as opposed to the thermal state, is that since you have some squeezing in one variable, so you can measure noise on the peak quadrature that's below shot noise, then this is a guarantee that there is some anti-squeezing noise on the other quadrature that's not correlated to any third party. In other words, measuring squeezing is a sign of purity of the state, if you wish. So the more squeezing we have, the more randomness we should be able to extract. And so that's what we did. We ran the same protocol with this source and a different amount of squeezing. As you can see, when the squeezing increase, we get to better entropy rates. The unconditional mean entropy is still higher here because there's some impurity in the state. And so if you have squeezing, you can increase the amount of randomness that you have. All right, that's basically it. So we demonstrated real-time self-testing QRNG based on non-classical light. We tested with different sources. And oh yeah, I forgot to mention the speed of this QRNG was quite limited. It's only like tens of kilobits per second. But we didn't really focus on speed since we are limited by the bandwidth of the squeezing we had anyway. But you can reach gigahertz by using a dedicated hardware for hashing, broadband squeezing, which now is available, and optical beam switching. And also this device can be miniaturized with on-chip squeezers and chromaline detections.
Okay, thank you very much.
All right, thank you.
So let's switch immediately to the next speaker. This is Qing Yan, and he will present his work on benchmarking and quantum random number generator with machine learning. Please. We can't hear you.
I think he is still muted.
Yeah, I don't know how I can. I know how to mute
okay.
people, but
not now that should work.
Okay, it's please go ahead.
Okay, so yeah, so thanks for the introduction. So today I'll share with you our recent work benchmarking QRNG with machine learning. So this work is done with my ANU colleague Asad and Ping Koi, and also ML expert Omid and Nan. So consider a case in 2012 where a wide spread of vulnerable keys are discovered, in particular by exploiting the entropy loopholes. For example, poor entropy sources, non-eligible amounts of the private keys are actually compromised. So this tells us that if you have a weak RNG for your crypto system, you are essentially leaving a backdoor to your supposedly secure system, as cryptography is only as secure as its weakest link. So this is what motivates us to use quantum RNG, where we can use the inherent quantum randomness in the device. However, as we have heard from ID Quantic talk from Felix on Tuesday, in reality, the state might not be pure, and neither do we have a noiseless measurement and environment. So as such, a QRNG must be characterized and also modeled properly to ensure that only the trusted entropy are extracted. So nonetheless, in practice, our device might deviate from the original modeling, such as unaccounted noise, residual correlations, or even wrong assumptions. And furthermore, imperfections from the extractor, such as an overly simplified post-processing or poorly chosen and extractor seed together, all this could lead to a not so uniform output. So as such, with the advent of big data and machine learning, it's not hard for us to imagine that an adversary can use such a technique to compromise the security of a QRNG. So there are, of course, methods such as health checking, entropy estimation, and statistical testing. However, it's reminded that all these methods are based on finite sets of statistical elements, and they could lead to, and they are also prone to unknown statistical behavior and also correlations. So this begs the question of, can we examine the underlying randomness without, say, opening out the box or without using a statistical approach? So in our work, we answer this question by turning into this adversarial tool of machine learning into a diagnostic tool. So the method we are looking here is, can we learn from the previously generated random numbers to predict the next output bit? So to do so, we train our deep learning model over a training set, and then we evaluate its performance over several test sets by comparing its accuracy PML with respect to the probability of most frequent values of, let's say, a training set, PG. So the key components of our deep learning models are as the following. First, we have the CNN, convolutional neural network, which captures the spatial information from adjacent inputs. So for example, with multiple convolutional layers, more high-level features can be reviewed. RNN is, on the other hand, can help us to capture the temporal information from a sequence of input. However, in practice, useful information can be too far away from the present, and RNN might have difficulties to do so, to remember it, just as human. So we use a long short-term memory to help RNN to deciding what to remember and what to forget. So we test our idea upon a continuous variable QRNG, where the entropy source comes from homogenic the vacuum fluctuations. With the dynamical range optimized, our RNG is secure against classical sign information and so on. So we now let's look at the result. First is the entropy of the classical with classical origin by turning off our local oscillator of the system, and the second is by turning it back on. So in the interest of time, let's just look at the case where the simple estimator of this PG max bin guessing is most different from the machine accuracy PML. So we see that by plotting, let's say, the power spectrum and the autocorrelation of the data, we see there are strong periodic traces and also some persisting autocorrelation. And in fact, the stage in our QRNG is actually a stage without low pass filter, where the aliases are still present. Hence, our machine learning attack utilizes these features in predicting the next bit. So finally, we also have a test where we put pseudo RNG and the quantum RNG side by side over both the statistical needs test and also machine learning benchmarking. And we see that there's an interesting feature here where for the CRNG, a congruential PRNG with a period of 2 to the power of 28, it actually passes the needs test, but it didn't pass the machine learning test. So in a sense, it couldn't hide its own true identity under the scrutiny of machine learning. So to sum up, you definitely need a good RNG for your cryptography, be it classical or quantum. And to this end, we put forth our ML benchmarking tool, where a designer can use it to diagnose the QRNG rigorously, and a verifier can also benchmark the raw and post-processed data with an algorithm-agnostic manner. And finally, for an end user, they can just test the entropy of their device with minimal system knowledge. So our code is also available on GitHub. And as promised in our longer version of the talk, we also have a tutorial version on Google Colab, which can be accessed here or talk to me later. So yeah, thank you for listening, and we will be glad to interact with you all later on. Thanks.
Thank you very much. So before we switch to the next talk, I would like to remind the audience that you can ask questions now by using this question and reply function. So please don't hesitate to ask your questions there to any of the speakers and indicate to which speaker you would like to ask a question. Okay, so now let's go to the next talk. It will be given by Fabian Beutel from University of Münster in Germany, and it's about broadband detector integrated QKD receiver chip for gigahertz clock rates. Please, Fabian.
Yeah, thanks for the introduction. I'm from the group of Wolfram Pernice at Münster University. On this conference, we've already seen quite a few talks on integrated QKD with impressive work. However, most of these works or the chips are actually focused on Alice, so on the sender side. And we actually also wanted to bring the benefits of integrated photonics to Bob. And the benefits, of course, are that you don't need to worry about alignment anymore. Also that it's much easier to stabilize a small chip, which is only very small compared to a big bulk setup. And finally, of course, most of the scalability issues disappear once you move from bulk setups to integrated fabrication process. And for integrated QKD, it's always very nice to actually work with time-based protocols or time and phase-based protocols. And for our implementation, when we actually built this chip, we designed it for these time protocols where you actually need to somehow check with interference. Yeah, you need to do some form of interference measurement, so you need this Mach-Send interferometer. And for our implementation, we actually chose this 3-state protocol presented by Hugo's group in Geneva, I think 2 years ago, where you basically have 2 bases, so the Z and the X base, and only 3 states. So you use the early and the late time bin and then the superposition state. And only this Z base is used to transmit information, and the X base is only used to estimate the phase error rate. This is relatively simple to implement, so it's a very nice protocol. And basically what you need is you need a splitter and then this Mach-Send interferometer, and then of course 2 detectors. And this part with the interferometer has also been integrated by other groups in the past. I think the O'Brien group has showed something in this regard a few years ago already. However, we also wanted to integrate the detectors on chip to really have one integrated package with everything on one chip. You also heard at this conference already that SNSPDs, so superconducting nanowire detectors, are basically state of the art with regards to single photon detection. And they have really matured in the past years. So they offer great detection efficiency, also really low noise. And just recently also people have shown a jitter of below 3 picoseconds in the lab at least. So this is really a very mature and promising technology. But when you, of course, what you have traditionally in this SNSPDs is this meander nanowire, and the light is incident from the top in this picture. And this is, of course, very difficult to integrate on chip. So what we use in our group is a slightly different technology. So we start with a waveguide here in blue in this picture, and then we just place this U-shaped nanowire here in red on top of this waveguide, and this actually absorbs then through the evanescent field, absorbs more or less all the light in the waveguide, depending on how long you make it. And this, of course, then allows you to add additional photonic elements in front of this detector. So it's perfect for photonic integrated circuits. And also it has the additional benefit, and this is also something Felix talked about in his talk, that one challenge for QKD is to make these faster, these detectors. When you actually have this design, you can actually, they are intrinsically faster since the wire doesn't need to be so long. So usually we have about 5 nanoseconds dead time. And you can even make them very short if you only use like a bow tie setup. And in this case, up to 2 gigacounts per second have been demonstrated by our group in the past. And so this all we integrate on our chip, which as a 3D rendering looks a little bit like this. So we have basically only one input that comes from Alice, and for the coupling from the fiber to the chip, we actually use 3D printed couplers. So this is really 3D printed onto the chip after fabrication, which is nice because it allows vertical coupling. So we can really address the whole surface area of the chip, which allows for many channels in principle. And also it's very broadband. So with this couplers, we can really couple in light from the visible all the way to 1600 nanometers. And then of course, it depends on the waveguide that you build. And then we couple most of the light we forward to the main SNSPD, and then about 10% is put into this MZI. And of course, if we talk about 200 picoseconds delay, this corresponds to 3 centimeters on silicon nitride. This isn't really long for fiber optics, but if you move to integrated optics, this suddenly becomes this huge delay line. And although we're on a low loss platform, we have some losses if you have such a long delay line. And this we balance out by adjusting the input splitter of the MZI. And then finally, we have the output where we measure the destructive interference with the secondary SNSPD. And this is what the chip looks like. So this is an SEM picture. And then here on top, you have a photo of the chip in real life. So you can see that we can place about 50 to 100 of these devices on one chip, which is about 15 by 15 millimeters big. So with this, we actually performed the experiment, and yeah, we kind of compared it to this implementation by Hugo's group. And we can see that in the for short distances, so for short small channel attenuations, we don't actually suffer from this dead time that APDs bring with them, since the dead time is really not really limiting us here. So we're not really saturating the detector, which is nice. In the long distance range, here the setup from Geneva is more sophisticated, since they have a lower error rate in the state production. But here mostly we're limited in the state preparation. For us, it was really a challenge to get a good extinction ratio on Alice's side of the setup. You can also see that at least in the Cuber, we're not really limited by dark counts, so this is relatively stable. Whereas in the phase error rate, where the counts are of course much less, you can see an effect of the detector count rates from about 25 dB. Yeah, then finally maybe sorry, I can go back. No, thanks. Okay, then let me just end with this. I think that's over time anyways now. So thank you for your attention, and yeah.
Thank you very much. Thank you to all speakers. And now we can go over to the questions, and this will be handled by my colleague, Felix. So
yes.
Felix, you collected the questions, so please go ahead.
Yes, we got some questions. So yeah, thanks to the speaker. All great short talks. Now we have time to dig a bit more with questions. So first of all, there's a question by Christian, actually, for Qing Yan. The question is, have other groups already used your machine learning test for their RNGs? Has it been used by others?
Yeah, so there are requests for the codes questions, but I think so far we haven't seen a publication that directly uses our code. There are publications that uses techniques similar, but exactly so not yet. Yeah, we are looking forward to it.
Okay. Yeah,
I guess it could also be interesting for classical RNGs.
Yes,
you know?
That's right. Yeah, so in fact, that's what we are also targeting at. Yes.
Yeah. Okay.
Okay, so we have another question from Gong Zhang, which is for Fabian. He's asking about the yield and the fabrication time for such a 3D printed coupler. How difficult is that part to make in practice?
So the machine which we use for this is a Nanoscribe. This is a commercial machine that you can just buy off the shelf. The fabrication time per coupler, right now it's about 5 to 10 minutes really, so it's not super fast, but it can be, so you can speed it up, and there's some work going on for this. And the yield, it's relatively high. So there's, you need some testing structures usually on the chip itself, where you start to finding the right parameters for the chip, but once you've found those, the yield is actually rather high on the chip itself. Right, I can't give a precise number for the yield for the couplers right now.
Okay. So actually, Sibo has a question. So for you, Fabian, he's asking, what's the material of the 3D printed coupler?
So it's some polymer. So it works by 2 photon absorption. We have different polymers actually that are used. So I would have to look up the exact polymer that was used here. Yeah, in principle, I can send you some link to a paper if you like. Then.
Well, maybe just a follow-up question from me on this. Do you have problem with polarization with this, or do you have to control polarization?
Yes, so not due to the couplers. So the couplers are really not very polarization sensitive, but of course the waveguides are. In our case, we usually are limited to the fundamental TE mode in one mode only. So we always only work with one polarization, and therefore we are also polarization dependent. But in principle, you can make also your waveguide higher and support two modes. And then, of course, you need to adapt the nanowire design a little bit. But in principle, this can also be done and designed in a way that you're not very polarization dependent anymore. So the couplers here are not the limiting factor, but the waveguide usually is.
Yes, okay. Which is in silicon nitride, right?
Yeah, we're working with nitride.
Yeah. Okay, so I have a question for Thibaut. So Yeah, okay,
Yes.
thank you for muting. So I'd like to learn more about the miniaturization challenges that you might have with your system. If you wanted to miniaturize, it's a CV or it's a CV-based QRNG. Is everything easily miniaturizable, or you have some parts that you think are definitely challenging?
Well, yeah, of course there are some challenging parts, that's for sure, but it's just a perspective to have. But yeah, it depends whether your detection is in free space or if you manage to integrate that as well, and the amount of loss that you include with the coupling. But so one of the main thing is that when you have on-chip squeezers, which, well, are not easy to make, but they are intrinsically like broadband because they're usually not inside the cavity, which makes them like more efficient if you use them in such protocols, because then you're not limited by the bandwidth of your squeezing. So I think in that case, it's interesting, yeah.
Okay, thank you. Okay, so we have more questions from the audience. There is a question by Roger Colbeck for Qing Yan. The question is, okay, let me just read it through.
Well, I think Roger can ask the question himself. He's already almost connected. So
sure, yeah, good idea. That's who is right there.
Yeah, so you showed an example where your method detected correlations where the NIST tests do not. So I think that was based on a random sequence that had some very long repetition rate, if I understood correctly. So I was wondering, what about the converse? So are there types of imperfect randomness for which your machine learning algorithm does badly or can be outperformed by other tests, for example, the NIST tests?
Yeah, I think that's a very excellent question. So we believe that, so if we look at our method, we are actually having a training set coming from the random number generator. So that means, in a sense, our method is actually agnostic to what the types of randomness inside. So that means we are actually depending, yeah, it's not input depend, it's not a fixed method, but rather it can adapt according to the type of, let's say, imperfection coming from the random source. So in a sense, we believe it can probably, it should be able to learn, but what type of randomness that our method might does badly, I would say could be, for example, if the range is so long that and the training data is not large enough to cover that correlation, then that could be what might happen. So for example, in the slide that I show, for one of the PRNG, pseudo RNG, we actually didn't crack it. And that's because the data size is almost the same size, or if not larger than the training size. Yeah.
Great, thank you. So another question from for Qing Yan by Nirai Kumar. So I will, yeah, he's unmuted. Great. Nirai, please go ahead.
Yeah, hi Qing Yan. So my question is, like, does your results imply that QRNG is like robust to deep learning attacks? Like, because in one of the plots you had like the probability of guessing was the same as the probability that the machine learning model was doing. And the second thing is that, like, have you also explored like other neural network structures? Like, do you expect like better performance of the ML model, like if let's say neural network is denser, or if you consider some other structures? Yeah.
Yeah, thanks. That's also a very good observation. Indeed, our QRNG itself, I would say here, as I also show in the slide, your QRNG is usually imperfect and there are noise. Your extractor might not be perfect, so on. So I would say when you by robust, that means if you have done everything properly. So yeah, it's a good test in that sense. So in fact, also throughout my slide, I also show that if there's some hardware that you didn't design properly, so your raw data might have some correlation before the hashing, and it might also screw the final output. And as for whether the ML performance can get better, so there are Actually, if you had a chance, you can have a look at our tutorial or the GitLab. And there are a lot of parameters where you can play around with for the machine learning. So for example, here I didn't explain about the step size. So you can also tune the overlaps between the learning such that if it's denser, usually it will be more accurate, but at the cost of longer training time. And it can take, let's say, half a day or so, depending on your hardware. Yeah.
Great, thank you. So it's 11:30. I think we don't have any more questions from the audience. So Hugo, would you be okay with finishing now?
Indeed. Well, I have a few questions for Fabian, but I think I can ask him the questions at the coffee break. So I think indeed we can close this session. Thanks again to all speakers and for the discussion. And we meet